Hello, everyone. We're here with our final application project for Group 30. I'm Lucas Fertig, and I'm here with Jack Homerson. So, our overview today, we have our introduction, project description, design implementation, interpretation of results, and conclusion. So, with our introduction, we're just talking about water resource management, and so that is a aspect of civil engineering consulting. And in land development, it's really crucial to design these like drainage systems and infrastructure in a way to handle extreme weather events. And we're using the Brunch-Kutta fourth order method and quadratic spline interpolation to model the mass balance in this specific case, a road and the water in and the water out. And we're using our spline interpolation to model our rain flow in. So the goal of this project is to just model the flow off of the road because of the rain. So we're talking about the accumulation of water due to extreme weather events, and we're going to vary the different inlet widths to drainage and the varying road area. And so we're using our program in our program of Runge-Kutta to solve our mass balance equation and our spline to interpolate the rainfall events in these scenarios. So we believe that these two methods will be able to simulate our rainfall and flow events to help better design and optimize different catchments and public water infrastructure.
Now for our design implementation, we went ahead and used the Runge-Kutta method. This helps us take the water depth on the road surface and treat it as a variable that goes over time according to the difference between the rainfall inflow and the drainage outflow. And the governing equation is shown below. This is where the inflow is interpolated from the rainfall data, and the outflow is modeled as a function of the water depth based on the storage threshold that is provided. This method tracks the water depth at each time step and ensures no non negativity using conditional logic. And then for our second approach of this project, we went ahead and used the quadratic spline interpolation. This is constructed by solving a system of equations and enforcing pointwise accuracy for the first derivative continuity. Now for the interpretation of the results, the two graphs on the left have to do with the Runge-Kutta. The top left having a inlet size of 2 meters. Some observations from that where the water depth gradually increases and starts to plateau around 50 minutes in that top panel. The interpretation of this is it shows ponding due to excess rainfall, where the inflow surpasses the outflow capacity, and this plateau happens. For that middle panel, that has to do with the rainfall input. This just resembles a typical storm event where the rain intensity increases, peaks, and diminishes. And for that bottom panel, this has to do with the drainage outflow through the inlet. Our observation was the outflow remains near zero for the first 45 minutes, then rises rapidly and peaks around 50 to 55 minutes. Now for the bottom left graph, we increased the inlet width to 4 meters. Again, in the top panel, the water depth on the road surface reaches a maximum of about 1 centimeter in 50 minutes, then levels off. Compared to the previous case with a smaller inlet, this configuration results in a slightly lower peak ponding for more rapid stabilization. Overall, this means increasing the width improves the runoff removal efficiency and reduces the maximum water depth on the surface. For the graphs on the right, we use the spline interpolation. The first top right one has to do with the road area of 20 meters squared. It basically just helps us predict how the inflow will go as the storm event occurs. You can see in that graph, increasing the road area resulted in higher inflow rates due to the larger catchment area collecting the rainfall.
To conclude this project, we just talked about how these numerical methods can be applied to model these stormwater runoff conditions, and we used our wrench cut of fourth order and the spline interpolation to do that. And we believe our simulation was successful in finding the most optimal way to do that. We increased our inlet width from 2 to 4 meters, which improved the performance by reducing the pond depth and stabilize the flow rates. However, that added cost could provide an issue, therefore, it'd be better to iteratively design this and create the most optimal decision for that engineering consultant. And like overall, these modeling techniques and different numerical methods could be applied to like residential commercial development on something like a land development design for a 100-year storm. And I believe we could tweak the simulation to provide answers to other important questions. Thank you very much.